week we talked about torques. Okay. All right. We had a problem where we had this thing here, right? We had a bar that pivoted around a point, girls. Okay. And we had, shh, I'm done now. I'm done. Okay. I know. Well, let's start to try to control it. Okay. Okay. So we had a guy, and he was pulling on this beam, right? Okay. Do you remember how we did this problem? We finished in this class. I know we finished in this class. Did we not? We did not? Come on, we didn't finish it? Okay. What? Okay. So let's do this quickly because I have another problem for you to do. You're going to do by yourself. Shh. So we said, let's just make up some. Does anyone have numbers, or should I make up numbers?
I have.
You have numbers? What are the numbers?
WT1 equals 100 newtons.
Is it the right one or the left one?
That's the left one.
Had 100 newtons?
Yes,
100 newtons? What was my right one?
120 newtons.
Okay.
And then L1 is 0.75 meters.
Where's L1? Over to the right one or the left one?
It's the middle. It's in between
From here?
the dot and
In
then
between the
left
pivot
box.
point and
Yeah.
The left box. And that's how many meters?
0.75 meters.
Okay.
And then L2 is 2.5 meters, and that's to the right. Yeah. And then L3 is 0.5.
L3.
Yeah,
L3
it's
is,
to the left. In between
left wing
the
to
person
person.
and the.
Oh, okay. All right. So if that's 0.5,
Does that mean?
no. So that's 0.5. That means it's 1.25 meters from here to here, right?
Yeah.
Okay. All right. So it's out of scale. I get that, right? Juliana. Okay. Eyes up here. All right. So, shh. Okay. So the question was, I asked you, what was the pull force? There's some sort of pull force here. Okay. And what was the normal force acting on the pin? Right? What's the normal force from the pin and the pull force? Right? Everyone with me? And we'll call this A, B, point C, and point D. Right? So we draw a free body diagram. Free body diagram looks like this. We've got a force coming down that's 120. Oops, excuse me. We're going to call this force 2. Is this force 1 or force 2? Is that 2?
Yeah, that's 2.
It's 2. Okay, we've got another force here, F1. Come on, F1. I had a normal force here, Fn. And then I had some sort of pull force. Let's just call it down for the moment. Pull force, okay? All right. So the issue is this. We know two things and we don't know two things, right? We've got we know F1 and we know F2. We don't know Fn, we don't know Fp, correct? And I'm asking you for those two things. So if we do a sum of the forces equation, like we normally do, sum of the forces, what direction are my forces, x or y? Y. So I would do that, say Fp plus F1 plus Fn plus F2 would equal what? 0 if it's not moving. My net force is 0. Some of my forces in the y are 0, okay? So we could do that, all right? The problem is what? What's the problem now?
There's 2 unknowns in one equation.
Right, there's one equation, 2 unknowns. So we can use another method to help us out. What was the other method we talked about last week?
The torque.
Sum of the torques. So we're going to do the sum of the torques. Now the question is, we do a torque is equal to what? Force times length. One thing I didn't mention last week, I want to be clear. When we say times length, is times length perpendicular. So the force times the length perpendicular to the force. In the next problem, you'll see what I mean by that. But yeah. So in this case, the length of Oh, the drill press? Okay. In the back, there's a red drill press. You can probably carry it yourself. You can go out that back door, okay? It's on the floor somewhere. You're welcome. Okay. Hey, girls, if there's a drill bit in the drill press, take the drill bit out. Okay. All right. So look up here, guys. Look up here. So my force to my weight is acting perpendicular to the arm at which it's of that 2.5 meters, right? Do you guys see that? The angle between this length and that force is 90 degrees, okay? In another case, you're going to see where it's not. We'll see how to deal with that in a minute. Okay, so when we talked about this last week, we said, hey, we're going to take the sum of the torques. What is torque? Matt Davis, what is torque? It's a rotational force. So we're rotating what? Around a point. A point. If everything's balanced, what are the sum of the torques equal to? Zero. What point did we sum the torques? What points did we sum the torques around to make sure it was zero? What? There's a key on the side. Use the key. Okay. Guys, Hunter, can you help them take the drill bit out, please? Okay. When we do the sum of the torques, in order for the sum of the torques to be zero, what are we taking the sum of the torques around? What point?
Any point. Any point.
Any point. If it's A, B, C, D, somewhere between C and D, somewhere between B and C, anywhere along this point, if we sum the torques around that point, they will be balanced and equal. The sum of the torques will be zero.
Like the lengths are in relationship with the point.
So if I am pulling on this side and I'm pulling on this side, they're going to be equal. But I can sum the torques around any point on that beam, it will always be zero. That's the key. Thank you, Hunter. Okay? So, here's the deal. The question, though, is what point is the best point to sum the torques around? That's the question. Tell me what's the best point to sum the torques around? What's going to benefit me? Guys. Oh, you're awesome. Thank you so much. And I think it's printing now. She does rock. Guys, listen up, guys. What is the point around which I want to sum the torques that's going to be beneficial to me?
Normal forces.
Okay.
No, one of them cancels it out.
Okay, Matt, you guys are right. Matt, explain that.
Okay, we'll see. You're trying to find FP and Fn, but you need, in order to find them, you want one of them to have a length of zero. That way it cancels out, and you can look at the other one and solve for only one variable.
Right. Does that make sense to everybody? Okay. So the issue is this. Ultimately, let's say I sum the torques around this point right there. Okay? If I sum the torques around that point, I'm going to have Fp times the length to this point, plus F1 times the length to this point, plus Fn times the length to this point, plus F2 times the length to this point. And that should all equal zero. But I'm still going to have one equation, two unknowns. Right? It isn't going to help me get anywhere. I want to be able to solve one for the other. However, the force at this point, there's a force at this point, but the length from the force at that point to that point is zero. And therefore the torque is zero. So if I wanted to be strategic about it, I could utilize one of the points that I don't know, one of the forces I don't know, and sum the forces around that point. You see what I'm saying? So let's say, you follow me? So let's say I did the sum of the torques around A. Okay? Let's go back. Actually, let's do it about C. Okay. A is where the guy's pulling. Okay, it's a pull. I'm gonna call this. This is A, B, C, and D, and this is nothing here. Is that cool? Okay. All right. So let's do the sum of the torques around C. Let's lay it all out. Let's do it in variables first, okay? So I have the sum of the torques around C. So my first force is going to be Fp, right? So it's going to be Fp. Do I know the value? I don't know, okay? Times the length from that to to C. Now notice I also have the dimensions too, so I already know that. So what's the length between A and C?
1.25.
Okay. Is that length positive or negative? Negative. If I'm left of the point that I'm rotating around, then it's going to be negative. If I'm right of the point I'm rotating around, it's going to be positive. Yes, ma'am.
Okay, so I still need clarification on torque. Torque is the derivative of acceleration.
No, not at all. No.
That's jerk.
That's what?
Jerk.
Yeah.
Jerk is the
Oh yeah. No, I don't. No. Torque is this. Ready? Torque is a door, and I'm pushing on the door with a certain length. I have to push. In order to push, this door has a weight and a work, right? I push here at a certain length to the pivot point. I'm pushing with a certain force. I'm making it open and twist. The twisting force is the torque. It's a twisting force. If I want to push this door and open it again over here, I have to push much harder to get it to open. Does that make sense? Shorter length, harder, bigger force. Longer length, shorter force. All of them equal a twisting force. Think of the force required to unscrew a bottle. That torque, that twist force, the amount of force I got to twist, that's torque.
So if you wanted to make, using that example, if you wanted to make opening a jar easier, you would...
What would be, if you want to make it easier, what are you stating is the thing that you don't change? What's the thing that you can't change?
Your hand.
Your hand. Well, what is the force, right? So if you can't change your force, and it takes you so much force here to open that door or twist that jar, what do you want to do? If you don't change the force, how do you make it easier on you?
Insulate between your, put something between your hands.
Make the length longer.
Right, so...
The length longer. So I could take this jar and make a bigger thing and actually make it open. That's why you get a lever. That's why you see the commercial for the jar opening thing, which is a big rubber thing that holds onto a big lever arm. Bing, and it's like a wrench. That's why wrenches work. Right? Thank you. Yes.
So longer doesn't mean make a bigger lid. It means like
Torque equals force times
length
length.
is the distance between your hands and the center of the lid.
If you have, it requires a fixed amount of torque to open that jar. If your force wants to be easier, then you can increase your length. Right? If the torque is fixed, if you want a lower force, you must increase your length. Does it make sense? Okay. Yes?
Okay, torque doesn't matter, but it actually does kind of matter to me because I got the answer with this last one. I think 0.75 is supposed to be 0.25.
0.75 plus 0.5 plus 0.75.
No.
I thought this was 1.25.
You had L1 is 0.25 and L3 is 0.5.
Yeah, L3 was from A to B, I think. That's what Imam was telling me. It doesn't matter. Just change the numbers. It'll be okay. All right. Shh. Look up here. Hey, guys. Focus up here. So FP is times the length from A to C, right? Yes?
You
Okay.
stole or
Okay. Plus, shh.
I care. That's just supposed to be served.
Hey, guys, you are responsible for this regardless. Okay? Torque, that's a torque around A, right? So we're going to, let's do this. Torque, we're going to say the torque of FP plus the torque of F1 plus the torque of Fn plus the torque of F2. Okay? If it's balanced, that all the torques are equal 0. Because that 0 really means a net torque. Right? It's equal to a net force times a net length. Okay? The torque around C due to force of Fp is going to be my Fp times my length from A to C, which is how far? 1.25, but because it's to the left of the pivot point, it is negative 1.25, plus torque of F1. So that means it's F1, right? And what's my F1 force? What's my F1?
100
Okay, is it negative or positive? 100 newtons. The weight? Negative 100 newtons times what's the length?
negative
Negative 0.75. Plus my normal force, which I don't know yet, times what's the length between the normal force and point C? 0. You guys see that? Plus the torque of F2. What's the torque of F2? Negative 120 newtons times a positive 2.5 meters. Does everyone see that? To the right of the pivot point's positive, to the left of the pivot point's negative. Force pointing down is negative, force pointing up is positive. Keep with your system, you're going to be good. So now I have negative 1.25 FP plus 75 Newton meters, right? That's my unit of torque, plus 0, because Fn times 0 is 0, plus 120 times 2.5, so plus a negative 300, right? Plus a negative 300 Newton meters equals 0. So now I have one equation and one unknown, right? So that means that my FP is equal to 300 minus 75 divided by 1.25 negative is negative 180. Negative 180, negative 180 newtons. Because that's meters times FP. Does that make sense? Everyone with me? Okay. So that means, am I pulling up or am I pushing up or pulling down? Pulling down. Okay. That means that 120 times 2.5, that torque is much greater than my 100 times 0.75 torque. So I got to pull down a little more just to balance it out. No matter what point I take the sum of the torques around, it'll always be equal to 0.
Wait, Mr. I didn't get that it was negative.
Which part? There's a lot of
You're
ifs.
doing negative 300 plus 75, which is negative 225, divided. Oh, because you added. Never mind.
Yeah, you got it? Okay, you with me? All right. So now that I have FP, what can I do?
Fine. Do some of the forces.
Yeah, I can plug this puppy back into the sum of the forces of my Y. So sum of the forces in Y equals negative 180 newtons plus my F1, which is negative 100 newtons, right? Plus my Fn, which is what I'm looking for, right? And then I'm going to say plus a negative 120 newtons, right? So now and that's all going to equal 0 because that bar is not moving vertically. So Fn is equal to 220 and 3, it's 400, right? So Fn is a positive 400 newtons. And that makes sense. That means that bar's going to have to push up 400 newtons. Does that make sense? Everyone clear on that? Okay. Good? All right. Yep. Thank you. All right, I'm going to erase this. This is good? All right, I'll wait. Go. You sure? I'm recording it. Okay. All right. Yeah.
So like force equals mass times acceleration, right? So like if it's a constant force, then like what's the acceleration? Is this acceleration like say it's 400 newtons? Like
Of force.
What is that? A force? Like what is that?
Here, where do I get that?
Like,
Yeah.
Is something constantly accelerating on that point?
I think the breakdown is like, how do I pull to get a constant force of 400 newtons and constantly get that, right? Well, that means you have to be pulling yourself, and the person who's pulling has got to be accelerating as well, right? The more realistic is to think about a thrust of an engine, okay? If I am thrusting, I am burning fuel, creating a thrust or a force of so many newtons constantly, and it's ideally not, and realistically it's not constant, it's going to vary over time. but you can create that thrust, or an engine from an airplane, right? You've got that thrust from the jet engine pushing you back, which really means it's pushing you forward. And that thrust is constant, or ideally constant, okay? And then as long as it's constant, it's going to accelerate, but it isn't, right? And so your acceleration curve is not constant and realistic. It's going to, reality, so you have to do, it's going to be a curve that's going to vary over time, and therefore your velocity is going to vary over time, and to the second derivative, right? And then you're going to have the distance is going to vary, so your derivative to get the distance, right? So that's where the math comes in. And when you're in acceleration, it's not constant. That's where the integration really happens. Yeah.
Do you use the derivative of acceleration a lot in physics?
No. No. I mean, no, because once you get past acceleration, you're looking at how acceleration changes. Unless you're doing a lot of, I would say, heavy trajectory calculations. So you're doing things. If you're doing dynamic systems, now you're getting into dynamic systems, and you're looking at control systems. Okay, proportional integral differential control loops. So here's an example. You had your robot, right? And it was following the light, and it was looking at one light, right? And it was looking at the difference, and it say, I have more light here and less light here, and it adjusted. Okay. So if I had a graph, and I wanted to get to this point as quick as I possibly could. Okay. What would happen is you would aim for that point. You want to get as fast as you possibly can. I mean, I could come up really nice and easy, right? But there's a lot of wasted time here. Okay, what if I think it went really fast, I can do like this, but then I'm gonna overshoot it, okay? Well, that's really bad. I'm gonna overshoot it, so I'm gonna go whee, like this, and settle down. Ideally, you're looking at something more like this, that comes up really fast, and settles out very quickly, okay? And so now and what you do is it's a PID, proportional integral differential control. It's actually a whole thing called lump parameter systems or dynamic systems that you can actually start to create a mathematical model to represent the equation and therefore the acceleration rate and the speed rate to get to do what you're doing. And this is not just in it's not just so all of the Google driving car, right? You want to keep it on a path and a trajectory, and you need to know where you're going, especially if you're going fast or going slow. That's what you're trying to do. You're trying to keep this line, this straight line is actually not, it's a guide path, and it's, let's say it's steering, right? It is the path of the road. And you want your steering to control nicely to always be on that. You're going to oversteer sometimes and you're going to backsteer, but you don't want to be doing this, because sometimes you can get out of control. And so you do a lot of that to get to that point. Does that make sense? I know there's a long answer to your question. But
Wait,
yeah.
Was the Google car a metaphor?
No,
or
no.
was that
Reality.
an application?
Oh yeah, perfect application for control systems. What you did with the robot is one of 3 components that's used in the Google car for control algorithms.
But wait, so that has to do with jerk?
It has to do with what it has to do is it has to do with function mapping. All right, you're trying to get to the same function. You're trying to get and recreate the same function. So if it's position over time, then you want to map. Let's say your position over time. Okay, here's time. Here's position. Let's say it's horizontal position. Okay, here's my center of my road. Here's my left side. Here's my right side. You're going to be doing this. Okay, you want to steer so that your car is following right along with it. Okay. But you have to do it with the control system. So you have to look at get the input, which is your light, and your output, which is your motor. And what you're going to end up doing is probably something more like this, right? But the closer you are, the better. And there's a whole Fourier transforms is essentially a way of creating a multivariable differential equation or multi-segment differential equation to actually recreate that same function.
But that's also
It's very cool. It's very cool. And by the way, and let's say if I want to control motor speeds for let's say I'm making diapers, okay, and everything's on a web, okay, and I'm going to have everything feed in and feed out and go over certain feed rates. I want everything to be the same. use the same algorithms to control the motors for each of the lines. I'm gonna put in the main web and put the second layer of diaper and the third layer of diaper, and they all have to work together and be at the same speed. Huh?
I think he's trying
Why?
to think origins of your exam.
I co-opted Kimberly Clark in Paris, Texas 1 year, and I worked in the pull-ups area.
I think he's a baby.
I wear diapers on the weekend. No. Okay. By the way, did I tell you my KDF knockdown flats story? Okay.
Oh my god, I thought you just said I knocked up my KDF. I was like,
What? No. I was in a meeting at Kimberly Clark, and in all these big companies they have 3-letter acronyms for everything. And so in these meetings, the cases, the cardboard case boxes that you pack all the diapers in, they call them KDFs for knockdown flats because they're flat boxes that knock. And I'm in the meeting, and they said, "Is there anything else that anyone wants?" I'm like a snotty little college kid. I go, "Yeah, I have something." I said, "If we're going to use a 3-letter acronym for a box, can we use BOX?" And everyone looked at me and was like, "Okay, let's move on."
You got it, Mr.
Yeah, buddy. All right. Okay. Next problem. Okay. Shh. Important part. Look up here, guys. Shh. Shh. Okay. Here's my lever arm, guys. Here's my force. Here's my length. Here's my length perpendicular to my force. You guys see this? Okay. However, if I had okay. Okay, these are the two same forces. These two values of forces are the same. Okay? Here's the deal.
wait, what does that say?
L prime, I'm just using it as a secondary L. Okay,
What's the first
not
one? L what?
L perpendicular.
Wait, so like that part is
Yeah, why are you using?
Because I'm going to let you know, as a standard in all engineering textbooks, prime is used as a secondary version of the first, not always as a derivative. Okay?
Why would you do that?
Because people run out of letters. They run out of letters. Okay. Okay. Let's do it. Shh. Let's do it this way.
Okay, you can just change that and put it down.
Okay. L. You guys complain, I gotta change. So here's my L. Guys. Shh. Hey. Matt, quiet. Okay. Okay. So I have my length of my arm with this F, L. I have length LX with this F. The difference is this F is perpendicular to L sub X, where in this case, F is not perpendicular to L. Okay? Now, if I'm going to have my torque equal to my force times my length perpendicular, I can do one or two things. If I look at the force perpendicular, force perpendicular, right? That force perpendicular is going to be less than this force, isn't it? Right? If I'm pulling this force, some of it's going this way, some of it's going that way. So that means if I have a torque, let me get the same torque, okay, with 1L, the perpendicular force would be less, or I can have the same F and have less L. Does it make sense? Okay? These force perpendicular, hold on. Force perpendicular. Let me call it something different so you guys are there. No, let's not say force perpendicular times L must equal Lx times force. Do you guys see that? Because if I'm going to if I'm going to create a torque, if I'm going to have the same torque around this point, right? I'm going to push like this. I'm going to push either perpendicular on the door, or I'm going to push at an angle. You see what I'm doing? I'm not pushing that way, I'm pushing outward. Okay? That means there's less force if I'm pushing outward at that perpendicular. So if I want the same torque around this point, then my L can be longer than this L, but my force is less. Trig, right? I have to apply the trig. I'm either applying the trig to the force or to the length. Right? Does that make sense? Okay, so if I have a length theta, right? It's going to be Lx is going to be L cosine theta, right? And I'm going to take that Lx times my force. It's going to give me my torque. Torque around A. You guys follow me? All I'm getting at is this.
Which point is A?
Just the pivot point. Okay? And all I'm suggesting is this. And again, if I look at this, right?
Wait, so are those the same torques?
Yeah, they're the same torque. If it's F perpendicular times L equals Lx times F, right? Because I have to, F perpendicular is really the cosine of theta times F, right? It's the same thing. So all I'm suggesting is this: for this next problem, you need to realize that all I have to do, in order to get a torque around this A, if I have a force that's at an angle, you can drop it down and get the horizontal length. This force on this bar is the same as if it was this force times this horizontal bar. You following me? No, Anna, you not with me?
You might just have to like.
Do the math? Let's do the math. Okay? Okay, here's my force perpendicular. This angle is also theta, isn't it?
Yes.
Okay? So there's my triangle right here. So if I look at, I'm going to draw that really. Here's my F.
Wait, what?
Here's my,
What kind of geometry that we should know that those two data are equal? 'Cause
yes. That should be geometry you should know.
I do not see that.
I really do that.
You didn't know that? Okay.
I don't see how that, I don't understand what rule that is.
Okay, because it's similar triangles. So it, how do I prove that? I gotta go back and prove that. Let's see. Shh. Because if this is this, right, this comes down to here, right? Then I know that this angle is the same as that angle, and therefore that's that same angle, right? So if I've got two triangles, I have, I didn't draw it hard enough. If I've got this triangle here, right? Here's my theta, and here's my phi, right? If that's theta, and here's 90 degrees, theta, phi. Well, here's theta, here's 90 degrees, that's phi, so it's gotta be theta. That make sense?
Yes.
Okay. So therefore, my f of t, f perpendicular equals f times the cosine of theta, right?
This is a bit much.
This isn't hard. Look.
I'm still stuck on theta.
Oh, it makes
Okay,
it
look.
a lot better with, like,
Perpendicular,
right?
perpendicular, similar triangles.
I get that.
So theta. So that must be some
Wait,
angle
how come
phi.
if they're both perpendicular, how can that make some similar triangles?
Wait. Because the angles are the same. Watch. Theta. Let's say this is 30. That's 90. What's this? 60. Right? If this is 60, that's 90. This angle must be 30.
Yeah.
Right? Okay. Similar triangles. So, and because of that triangle, right? If I know that's the case, if I look at this force, it's actually, what you have to do is you have to actually cut it here. Okay? And we're looking at this. This perpendicular force is F times cosine theta to be F of perpendicular. It's the same thing as Lx. Lx is L cosine theta. Right? So, it's either going to be F cosine theta or L cosine theta. We're going to have to do that cosine theta proportion to get the same torque. Does that make sense? And all I'm suggesting is this. If I have a bar like this, and I have a force coming down, F, okay? And here's my L. The torque around A is equal to F times Lx, or L, where Lx is L times the cosine of theta. Okay? So in other words, it's like dropping that, because it's a vector, right? I can drop that vector down because again, torque is equal to force, is equal to force times the length perpendicular to that force. This force is not perpendicular to this length. It is perpendicular to that length. Does that make sense? So I can shorten the length to get that same torque. Are you guys with me there?
Yeah.
With me? Okay.
I
All right.
like am pretty much with you, I think, but like in that
Like
I
why?
understand each step kind of as you're going through it, but like if you were like going to do problems with knowledge or
Okay.
like,
We're gonna do this. All I need you to know is you can. All I want you to do is believe this right now, right? You saw the math,
okay,
right? You believe the math,
yes.
and so here's the deal. The force. So if I have a situation on this, I'm going to show you an example where this is it, where this comes up. But in order to solve this, you could either solve for F perpendicular times your L, or you can drop the F down and just figure out your the LX component. Okay? Yes.
Wouldn't it just be T equals length S cosine theta?
Yeah, and that you can pull it out. I'm just showing you. I want to show the concept why it's one is yes, right? Because it's you're pulling it out. But here's and I'll show you why we're gonna get there. All right, so okay, so here's the example we're gonna run. All right, what we've got is we're gonna have a little wheel, okay? We're gonna have a ladder here, like this. All right. Okay. So this ladder's on this wheel, so there's no friction up here on this wall. Okay. And there's an angle between here and here. Okay? Let's say, I might do this, I'm going to do this a little bit, I'm going to draw it slightly differently.
Oh my
Oh,
gosh.
stop. Oh, stop. Just to clarify a little bit better, okay? That's all I'm doing. All right. Can't you do this on your paper? Okay. Here's the thing. I've got a couple things going on. I have the weight of the ladder, right? F of G of the ladder. Now remember, I don't know if I did this in this class, but if I have a meter stick, where's my meter stick? Okay. If I think of my meter stick, it has a weight, right? Okay. It weighs the same in my hand if it's here or if it's here, doesn't it? Right? It's either up, it weighs the same as if it's here. Had my eyes closed and it felt the same texture, I would never know the difference. Okay, I feel the same amount of weight. So any object of uniform density, okay, can be treated as if it was a point force directly in the middle at the center of gravity. Okay? So any object with a uniform, let's even not even uniform, any object can be treated as a point weight force at its center of gravity. In a uniform density, it's the middle, right? If it's something that's not uniform density, then you forgot the center of gravity. I see the bone breaking. Okay. Does that make sense? Okay. Beautiful. Isn't that nice? Okay, so the ladder has a center of gravity in the middle, always pointing downward. Here's the downward force at the length that's not necessarily perpendicular. Okay. In addition, I have the alien. Guys, you need to finish this for homework, okay? Hold on. You're gonna finish this for homework.
That's no alien, that's correct.
Okay.
Can you throw
That's no
right
alien.
here
That's
like
no
us, like alien?
Wait. Don't go. Hold on. Shh. L equals, shh. Wait. 1.5 meters. LA equals 1.2 meters. The L of the FG of the ladder is equal to 10 newtons. FG of the alien is equal to, actually make that 15 newtons. 10 newtons of the alien. You need to determine the mu of static friction so that the ladder does not slip. All right. You're going to need to do some of the forces and some of the torques. Have this tomorrow, guys. It's due tomorrow. It's due tomorrow. You guys took some time. It's due tomorrow.